and you do BV. And so let me remind you, so the motivation for BV makes sense of this integral on some spatial fields when the action is degenerate, so there are symmetries, so I mean the Gaussian perturbation doesn't work because the quadratic Hessian around the critical point is degenerate. So what you should do, for example, in this case, there is a group action, you might think of doing, well, you just replace this as a volume of the group, time an integral over the quotient. Okay, the volume of the group is not well defined, it will be also some infinity. Anyway, this is just a normalization factor, say I integrate over the quotient. And the problem is that the quotient is not very nice typically, and certainly it's not a fine space, so it's big, everything becomes more complicated. So the first observation by Faddeev Popov is that, well, instead of integrating over the quotient, so let's here, right, what you do, for example, suppose you have a group action, instead you choose some section of the group action, and instead of integrating over the quotient, you integrate over this section. And you have to be careful. In principle, here you assume that there will be some, well, we have to define a dimension. Suppose that this here the back measure, so you have to make a change of variables because here you want to put a hard measure, and then you have to find what is the measure here. So there is some correction to the measure, and this is actually okay. This is a change of variable, some determinant. And Popov realized that this determinant can be rewritten as some other thing, which is now becomes fermionic. So the point that, well, the reason why you want to put a fermionic integration, of course you could get a determinant also by usual Gaussian integration, but the point is that you want to keep locality, and so if you do a fermionic integration, you put directly the operator in the quadratic form, and you produce directly the determinant. The Gaussian integration would give you the inverse, so you should put the inverse in the Gaussian part. This is not very nice because it becomes non-local. And so this was the answer in this case. And of course, it's obvious that it doesn't matter which section you choose, because this is by definition the same with integrating over the quotient. However, the idea that, well, can you check this directly? And basically, this was proved by Becky, Stora, and Putin. Somehow the idea is that, well, now you're already in some graded world because you introduce some additional fermionic variables, so you can construct some complex and show that if you deform this section, you change something here by something which is exact, and when we come out of this, becomes a total derivative, so nothing changes. Now this is an interesting step forward because you no longer need this interpretation. You can directly check that the result here is invariant under the formation of this choice. And you can already generalize it to the case where this bundle is non-trivial. Because like here you're making not only this, here just make the assumption that you have a group action and you can take the quotient, but here when you choose a section, you assume that there is a section. Which means that if you regard the map from F to F modulo G as a principal bundle, you're assuming that the principal bundle is trivial, which is not true in, for example, in Young-Mills, right? This is a group of ambiguity, which means that, well, equality does not work, but what works is that, well, maybe you find some sort of section, but which has multiple intersections. And then you no longer have this geometric interpretation, but you can check directly here that if you deform the section, the result does not change. So you can make sense of this part. Okay, now the problem is that, why do you need to go to DV? Well, one reason is that sometimes you don't really have a group action. You have some more complicated symmetries, just some distribution of symmetries, essentially, well, distribution in the sense of like distribution of vector fields, or well, distribution of some bundle of the tangent bundle. And this distribution is typically not even involutive of shell, so things can go really bad. But Alan Bekovitsky were able to generalize BRST in a way that works in these more general cases. The other advantage of BAV is that it has nice structure behind. Here you get some differential graded symplectic structure. this, well, yesterday, well, it comes to degree -1. And it has one advantage, one further advantage, that it is compatible with partial integrations. So we'll see in a moment, BRST turns out to be a special case of BV, where certain things are linear. And the point is that sometimes you don't want to do the whole integration to compute the partition function, but you want to do some partial integration, for example, to produce effective theories. And when you do this partial integration, even if you start from BRST, you get nonlinear terms that you don't want to have in BRST, but which are completely allowed in BV. So it becomes a general formalism you have to show. And another thing that I will describe, that also BV is very nicely compatible with the boundary BFE construction described yesterday, and so you can now relate them, and you can make sense of like these integrals where you fix boundary values in an appropriate way, actually parameterized by boundary values, so you really get a state for the system, a state, I mean, a boundary state. Okay, so this is the idea. So now let me just explain what the BV formalism is, and let me now do it first in a finite dimensional case. So it's easy to see, but there are theorems, and then the idea that we have to try to extend it somehow to the infinite dimensional case. So, and actually first locally, so say that eventually it will be symplectic manifolds, but let me start locally in the book coordinates. So we have some even coordinates, which I will call Q1 up to Qn, and some odd coordinates, which I will call P1 up to Pn. So we should think this as coordinate in the momenta. And these are coordinates of some open subset over n, and these are just the formal coordinates. So what does it mean to have, well, even odd coordinates means that, well, we consider a function of the PQ variables. This is actually a smooth function over this open subset, a smooth function of the Q variables, and then a polynomial in the P variables modulo the anti-commuting relation of the variables. Okay, just say that the P variables anti-commute with each other, and they still commute with the Q variables. Okay. Now, once you're here, you can define an operator which is just the sum of second derivatives with respect to the P variables and the corresponding Q variables, so the same index. Okay. So, well, the derivative with respect to the Q variables is the usual derivative. The derivative with respect to the P variables is just about the formal one, just impose the Leibniz rules on polynomials, and you just have to be careful with the signs. I mean, the derivative with respect to the P variable is also an odd operator, so when you go through some expression, you get signs when you apply the Leibniz rules. Now, an obvious property of this operator, well, this is sometimes called the BV Laplacian. That was the name they gave it to these quantities. Some people complain it's not, because it's not really Laplacian, but I mean, it looks like a Laplacian the way you write it, but it doesn't have a property a Laplacian. And well, one important property it has that it squares to 0, because when you apply this expression twice, right, you have two derivatives applied to Q variables, two derivatives applied to P variables. The expression is Q symmetric in the P variables and symmetric in the corresponding Q variables. So, 0. It has other useful properties. So, for example, when you apply it to a product of two functions, right, you have apply, well, this is second order operator, but well, one thing you can do is to apply both derivatives to the first function, or both derivatives to the second function, and there will be some sign depending on the degree of the function. But then you have also the possibility of applying one derivative to the first function and the other to the other, which means that you will get some expression which up to signs will look like some derivative of f with respect to P variable, derivative of g with respect to the Q variables, and then plus or minus here as well, and derivative of f with respect to the Q variables, derivative of g with respect to the P variables. There will be some expression of this kind. So this formula with the proper sign is denoted by this round bracket, and you get this round bracket here. So this is called the GD bracket. But if you geometrically look at it, well, this is the same expression you have for the Poisson bracket in usual symplectic geometry, and this is actually, the Poisson bracket associated to the symplectic form dpi. You have these two forms in terms of these even and odd variables, and this is the associated Poisson bracket. Okay, so this, well, since this form is odd, this becomes an odd Poisson bracket, which means that, well, the signs were differently with respect to the usual one, but okay, we'll not care much of the sign here. So, okay, the nice algebraic fact here is that if you think in the symplectic geometry, usually you have the symplectic, the Poisson bracket. In this version, the Poisson bracket is a less fundamental object in the sense that it is generated by a more fundamental object. Okay. Okay. So then another property that you can check, that if you apply delta to the odd Poisson bracket, it becomes a derivation here. So this here will be delta f capital G plus minus f delta G. There are no additional terms. Okay. And maybe one further thing you need. Suppose that you apply delta to an exponential, and suppose that this phi is an even function. Then you can see that, well, these are derivative of the exponential are again exponential times something, and so I can factor the exponential here. And again, you have either a possibility. So first you have to differentiate phi once, so back to the q variables, and then you have to put the second derivative, and you can put it again over phi itself. So you just get delta phi times the exponential, or you can differentiate again the exponent. And then you see that basically you recover this expression, but, well, half of it only. So here you get the bracket of phi with itself. Now, here this is not automatically zero because, okay, phi is an even function, this is not bracket, so this is a non-trivial expression. Okay.
For like an odd function, is it just like delta e? Is it just like the delta phi term, or?
For an odd function?
Yeah.
Well, for an odd function, this would be just 1 plus phi. Right?
Oh yeah, okay. Fair enough. Yeah, okay.
What to say, it's not very interesting. Okay, now let's come to the main application, which is a VV integration. So, well, basically the idea is to suppose that here we have your position variables, here you have your momentum variables. It turns out that what is nice, as nice property, is the integral of essentially the graph of a function which has good property with respect to the symplectic form. So it's called a Lagrangian graph. It is a graph that is also a Lagrangian submanifold. Now, in this setting I started with, well, I declare this Q to be the position and this P to be the odd variables. There is not much you can do because, I mean, if the position are even and the momenta are odd, the Lagrangian submanifolds are, well, either the zero section or the vertical things. Which are certainly not graphs. So the only graph is a trivial one, so this is not very interesting. So it's better now to pass from the original PQ variable to some new x, y variables. So I will think of, let me see which one I want to see. I want to see these as positions. So we put y here and these as momenta. I don't know why I chose this stupid convention, so okay, but this will be y and this will be x. And these are just some relabeling. So what I do is, so for some indices I define xi as pi and yi as qi. Nothing changes. But for the other indices, I do the opposite thing. That is, my xi will be the qi variable, and my yi will be the pi variable. Okay? So anyway, the same index pair, two coordinates, position and momentum, right? But with respect to the original one, I shuffle things around. So now I have some odd variables also here. Okay? What this transformation does, which is interesting, is that it doesn't affect the signs. So I can still write the symplectic form as dx dy, and I can still write delta as to the second derivative of this dxi dyi. Really, this operation does not change because, well, whenever I do something here, I exchange one even variable with an odd variable, so there are no signs. Okay, so now the idea is that, okay, I want to see this as a graph of some function psi. Actually, well, not really the function psi. So, well, the deep psi, in the sense that, well, I want to see the moment as derivative of the coordinates. So what I do, I pick some function psi of the y variables only, and up to sine, I set xi in appropriate sign to be the derivative of psi with respect to the corresponding y variable. Okay, so the signs have to be chosen in such a way that the expression, so dxi dyi becomes, actually, let's see, the expression xi dyi becomes the differential of psi. So dxi dyi becomes 0. Okay? So there is a unique choice, okay, up to global choice of sign that makes this work. Okay? So I will not specify the sign, but you have to be careful. So depending whether y is even or odd, you have to put a different sign here. Okay, so actually, okay, I think probably I have the sign, so I can tell you what the sign is. This.
Sorry, how does this why does this imply that dxi dyi is 0?
So if you set xi to be -1 to the degree of xi times this derivative, then when you compute this expression, you get the differential of psi, which means that geometrically, when you restrict the one form x dy to this graph, right, it's exact, and so its differential is 0.
Okay.
So when you restrict the two form, you get 0.
Ah, yes, okay.
So this is really random. Now, at the moment, this is a mystery why you want to do this, but I will just show you in a moment what are the nice algebraic properties of this. Okay, so okay, the idea is that what you want to do is to integrate. Now you pick some function f of both x and y coordinate, and you want to integrate it over this Lagrangian sum manifold. Okay, so this is about the geometric motivation, but actually this is something very, very concrete. Basically, you define what it means to integrate over here. Simply means that you take your function of two variables, you set the x variable to be the derivative of psi with respect to y, this formula, you just plug this in, okay, and then you integrate in the y variables. Okay? So this is the algebraic expression. Well, you don't need geometry, we just have told you that start with these weird things with even odd variables and consider this kind of integration. Okay? You define, you set the x variables to be derivative of a given function psi with respect to the y variables, and then you're just left with the y variable you can integrate. Now, here some variables are even, some are odd. For the even variables, you use just the usual algebraic integration, and for the odd variables, you use the Bayesian integration. Does everybody know what the Bayesian integration is? Yeah. Okay. And now let's come to this fundamental lemma. Will be the lemma. So this says the following. So if the function f is delta exact, so delta of g, and g is integrable, So integral means integral in terms of the even variables. For the odd variables, there is no problem. Then the integral of f over L psi is equal to 0, no matter what psi you chose. And this is probably the only thing you have to prove in this business. I will not give you the complete proof, just because I want to care much with sign, but it is very, very simple. So the idea is the following, that basically you want to relate the restriction of delta G to L psi with something where the derivative is out. So the restriction is something like you take the two derivatives, so they just write partial lower I and upper I to denote the derivative with respect to the x and y variables. Okay. And you want to restrict this to having this condition. So this is what you want to put here, right? You take delta G and you plug it in here. So this is the expression you want to have, right? And you want to rewrite this as sum over I, the I, and then the upper I restriction. Okay, so these two expressions are not the same, right? Because here I first take the first derivative, so these are the derivative with respect to this should be the derivative with respect to the x variables, right? And then I want to take the derivative with respect to the y variables, right? But now, right, since now the x variables, so of course one term will be here, right? That's just to take the derivative with respect to the y variables. But if I make this substitution first here, then the resulting x variable will depend on the y variables. Okay? So when I take the derivative with respect to the y variables, right, I will have also to differentiate the x variables and plug in this expression. So there is some other expression which is a bit complicated. So we have this derivative you already had, but then you have to take some other derivative with respect to other x variables, and then you have to take the derivative with respect to the x variables as function of the y variables, and then differentiate with respect to the y variables. Okay? So this is, per side it will become the second derivative of psi with respect to some x and y variables. So this y will be the same as this, and this. Okay? And so we have this complicated expression, and the nice thing you can check that, well, because of these signs, this precise sign you put here, and because of the parity of the coordinates, this expression is 0. Basically, at the end, like it's a sum over two indices. At the end, you see that there is one part which is symmetric, what you have here, and another part that you get here, which is skew-symmetric. So notice that this does not look skew-symmetric, right? But there are additional signs that are the sign you put there. So this part becomes skew-symmetric. So this is 0. So the conclusion is that taking delta G and restricting is the same as taking first the derivative with respect to the x variables, restrict, and then take the derivative with respect to the y variables. Okay? So this means that now the integral of delta G over L psi is really the sum of partial derivatives of something, and this is 0 by Stokes theorem. Okay? The Stokes theorem holds trivially by definition in the Berezin case, and in the back case, we make it work assuming that G is integrable, so it's half decay, and so on. Okay. So this is basically the only technical fact you need about BV here, and it's just now this is an immediate consequence, which is even more interesting. I mean, this is already interesting with sin application, but there is an even more interesting one, which is what we need for the applications. So we'll call this the BV theorem, which is the following. Now, suppose that you have a family psi t. So this is the family of I think you have to tell you that this psi must be odd. You see it here. the x variables have opposite parity with respect to the y variables, so psi has to be odd. Okay. So that's why, okay, in the physics literature this is called the gauge fixing fermion. So we see why it is related to gauge fixing in a moment, but it's called gauge fixing fermion because it's odd. Okay, so suppose now we have a family of gauge fixing fermions, so family of odd functions of the y variables, smoothly parameterized by some variable t. So this some variable, say, in some interval, so this is even variables. And then suppose that you have a function f of x and y, which is integrable, say, on every L psi t, and is delta rho. Okay, so these are the assumptions. Then what you can do, you can take the integral of f over L psi t. This is well defined because it's integrable by the previous expression. And so you will get a function of t, and you can compute the time the t derivative of this expression, and the result is 0.
So this is like the family of psi ties is a homotopy in T, or?
Yes.
Okay.
Well, it's more homotopy, or differentiable.
Okay. Yes.
If you want to differentiate. Okay, so the meaning of this theorem is well, similar, of course, to Stokes' theorem, somehow that if something is close, then the integral is invariant under deformations. And here there was a similar something, exactly integral is 0. And okay, so yeah, with this, and the proof is just an immediate application of the lemma. It's a bit sketchy. So how do you prove this? So okay, let me call this integral I sub t. So I sub t. So okay, explicitly I sub t is right, f restricted to x derivative of psi t with respect to the y variables at some signs. So when you differentiate this, well, where does t appear? T appears inside the x variables here. So we have to take derivative of f with respect to some xi variables. Right? And then you have to take the derivative of the x variable with respect to t, which means that you take psi t dot and differentiate with respect to the y variable. Okay, so you get this expression here. Okay, now, well, this expression looks like the Poisson bracket. It is a Poisson bracket, actually, right? So let's continue just with this expression. These were up to sign. This is f bracket psi. Notice that it's only one term. So here I take y derivative of f and x derivative of f and y derivative of psi dot. You don't have the other term because psi only depends on the y variables. So this is already the Poisson bracket. Okay, and now the idea is to rewrite this as delta, again, up to signs, a delta of f times psi dot, and then I have to subtract delta f psi dot and f delta psi dot. Now, this is 0 by the assumption. This is 0 because psi depends only on the y variables. So the result is that this is an integral of delta f psi dot. So now we have the integral of a delta exact expression, and this is it. Okay, so it's just a consequence of the lemma is the homotopy property. Okay. Now, well, what is the application? So let me first go to the intermediate application and then go to the real application. The intermediate application is a full wheel. So suppose you have the following data, some reference psi naught, which is for some reason what you are supposed to do, which gives you some reference L psi naught, and a function f, which is delta closed. And suppose that somebody tells you that, well, suppose you don't know yet this, suppose that somebody tells you that you will have to integrate this f on L psi naught. Okay, so you're given this problem. But this integral does not converge. Okay, so for some reason you want to compute this, but the function is not integrable. Okay, but then you realize that your function is delta closed, and so what you do is to pick some family psi t, which contains psi naught, such that f is integrable for t different from 0.
Sorry, what is the word before psi naught? Ref?
Sorry?
What is the word before psi naught?
So you have some reference.
Okay.
Psi naught that is given to you, and you're supposed to compute this integral. Right? You're given this task, but this does not make sense because the integral does not converge. But then you realize that your function is delta closed, and then you can, and also you can see your psi naught as the t equals 0 value of some family psi t with the property that f is integrable for t different from 0. Okay? So then instead of computing this integral, you say, well, I compute it as L psi t of f. Right? This is now well defined and does not depend on t. Right? So this would be for I naught, which does not work. And then you say, okay, I define I naught to be, well, IT, so t different from 0. And it doesn't matter what you put because of the theorem, this doesn't matter. Okay? So the idea is very similar to what you do in algebraic topology. For example, one thing you want to do is, for example, when you, let me do first complex analysis. Similar to complex analysis, I suppose that you have some function, one real variables, and you're supposed to compute the integral, but this function has some singularities, so you cannot do it. Actually, the integral does not even converge. But then you realize that, well, your function is the restriction of a holomorphic function, and then what you do is, well, you decide to deform the contour. Instead of integrating over a real line, you avoid the singularity, and of course there is some choice here. But then once you made this choice, right, you can keep deforming, right? It doesn't matter, and the result is always the same. So there are some, okay, up to moto p there are choices. You decide, well, where we go around the poles, but once you made the choice, it doesn't really matter which contour you choose. It is essentially the same idea. So again, what I'm saying here, that is not completely well defined in the sense that you might have different families containing psi naught, for which, well, this problem becomes well defined. So they will give you different answers in principle. So there are different classes of gauge fixings, but inside each class, it doesn't really matter which the representative you choose. So you can deform them. And in
the difference to the previous lemma is that like psi t is smooth except at t equals 0?
Yes.
Okay, yes.
Yeah. Or, for example, for positive t, for example.
Yes,
okay, so. Okay, so. Now let's go back to.
So one question in this family psi t that we choose, does f have to be integrable for every other t?
Yes, for every other t. Well, for every other, for example, for t positive, well, it's enough to say t positive.
So it cannot pass through t's where f is also not integrable, and then.
I mean, no, it has to be integrable for the other t's in some neighborhood of 0. Okay, so, so the application in field theory, which becomes infinite dimensional, so let me tell you what is the idea, is that, well, the thing you would like to integrate, so this would be our, well, partition function, right, is the integral over the space of fields, and you know that this does not make sense. Now what you do is to essentially, well, but roughly speaking, realize that the problem is because of the symmetries. So what you do here, you put additionally the space of symmetries. So let me, like, for example, suppose there is some Lie algebra acting as infinitesimal symmetry, but could be more general, and you make it odd. And the reason is that now this integral is a bit better. So this, okay, this was the original integral before. Now we deform it to something we call I0, which is this new expression. Now, why is this expression better? Well, because this integral was a bad one, right, which diverged. But now I add some odd variables, which do not appear here. So the integral becomes 0. So now this becomes infinity times 0, but you have the correct 9 times of infinities and zeros. So you added exactly the number of zeros that should compensate the divergent integrals here. Okay, so this looks a bit better, and the point is that now you should think of this as a Lagrangian submanifold of the, well, odd cotangent bundle of the space. So it's a zero section, right, of this odd cotangent bundle. Now the idea is that if you can see your original action, right, as restriction to the zero section of some new action we call SBV, such that delta exponential XBV is 0, then you're in business, right? Because then what you can do is, instead of this L0, you take some other LT, so you deform the zero section, making sure that now the integral works, and now it doesn't matter which T you choose. Okay? So this was our reference Lagrangian, the Lagrangian that is given to you by the physical problem, and then you deform it, and you know that you can deform it, and then it doesn't matter once, okay, when we class how you deform it, if you have this equation. So this is called the BD quantum master equation. And notice that the goal is, of course, you don't know what this BD action is at the beginning. You only know the classical action, right? It's like in the problem complex analysis. Here, right? You have some here, right? You have some function of a real variable, but you want to see it as a restriction to the real axis of a holomorphic function. Okay? So a priori it's not true that this is the restriction of a holomorphic function. So also here, you have to be careful. You have to be able to show that your given function is the restriction to the zero section here of a function that satisfies this equation. Okay, so there are some theorem already by BV that tells you that under some assumption here, this problem is solvable. Essentially, the point that you have to put all the symmetries here, and then it works. Okay, so this is called the quantum master equation, and okay, modulo the fact that now we are in the infinite dimensional case, so it's not clear what's going on. This works. Now, let me just spend a few words. How do you make it work in the infinite dimensional case? Well, the point that there are two things that are not defined: the functional integration and also this delta operator. So remember, in the finite dimensional case, it was a sum of the set of derivatives, infinitely many variables, something wild. There are geometrical ways of defining this delta. I didn't tell you, in the finite dimensional case, you can see that delta F has a nice geometric interpretation. What you can do, you can first compute the Hamiltonian vector field of F, and then you can take the divergence with respect to the back across Bayesian measure locally, and or up to factor 1/2 and probably sine, this is delta. So you have this nice geometric definition. I think it's due to Hudarabian. And this is nice because you can make sense globally. Now, if you have a global odd symplectic manifold, you have both the notion of Newtonian vector fields. What you need is some Bayesian to make sense of the divergence. And then you can write delta globally this way. The Bayesian must have some good properties so that this delta still squares to 0. I mean, locally should reduce what you have, but also it must have this property. But then here you see that what is the problem in the infinite dimensional case? You see that exactly the same problem as the functional measure. You need it here. So the two problems are related. So essentially you solve them together. So once you make sense some way of this integration, you also make sense of this delta. So you have basically you have to go to some regularization, and the regularization works both for the functional integral and then you have to be sure that it works in the regularization and keeps working, blah, blah, blah.
Sorry, how does this equation work in the simplest example, say 2D Young Mills?
I mean, you have to write it down, yeah. Yeah, we can discuss the example here later, yeah.
In practice, how does this connect to the FADEF-Popov method? Like if I start with a classical axiom and introduce the gauge fixing and the costs, is it obvious that then I will arrive to this BV axiom that satisfies the
No, this is a bit more. What it means that, so first you get this BV action, then you have to choose a Lagrangian some manifolds here. So if you choose it like corresponding to the way you would do it in FADEF-Popov, then this restriction turns out to be exactly what we have there. It works in that sense.
The choice of different families, what does it correspond in the BRST procedure?
Well, different choices of gauge fixing. So for example, I mean, the idea that okay, typical physical problem, you take some gauge fixing, say Lorentz gauge, but then you somehow you add some parameters. Well, these are the T that I have here. It could be more parameters T. So you can let your gauge fixing depend on parameters, and this procedure tells you that you can change the parameters. For example, in topological field theory, one thing you do is typically to choose also some Lorentz gauge fixing, but there is no metric to start with in the topological field theory, so you choose a metric to make your Lorentz gauge fixing, and then this procedure will show you that is formally that the result does not depend on the choice of metrics, so the theory is still topological.
In the FADEF-Popov construction, the anti-ghost kind of has the role of like a multiplier field to like enforce that the ghost satisfies the residual equations of motion for like the chosen gauge fixing.
Yes.
How is the situation here for like ghosts and anti-ghosts?
So
what is the role kind of?
So here you don't see it.
Yeah. This is more obscure, right?
This is more obscure. So what I told you that okay, there is a minimal thing you can do is just okay, start your original fields. Add the ghost for the symmetries, go to the odd cotangent bundle, which means you add with it
anti-fields and yeah.
And you make sure that you solve this equation. Now you have to choose some Lagrangian some manifolds in here. Right? Now the problem is that typically it's the Lagrangian some manifold you want to choose is not really a graph of what you have here. Especially in those examples. So what you do is actually you enlarge this space. So you put this space into as a section of a larger cotangent bundle. And you put some extra stuff here. And you make
like
sure
anti-ghosts that
exactly. So you make sure that the extra structure you add here is cohomologically trivial, in the sense that well, with this delta moment we see they produce some BRST operator, and the BRST cohomology here is trivial. So somehow the idea that well, making the integral over larger space is the same as a lower one. But now here you can choose a Lagrangian section, as I said before, with respect to these additional fields. And this corresponds geometrically to choosing Lagrangian submanifold here that are not graphs.
Okay.
you could formulate the problem, like you could formulate the usual gauge fixing by saying that you're choosing some Lagrangian, some manifold here, which is not a graph here, but it's a graph here. And for the computation, it's easier to have a graph. So geometrically, in the semi-classical version of this is this old idea goes by Alan Weinstein that there are, well, you consider a Lagrangian some manifolds, and in a cotangent bundle, that's nice. The nice ones are the graphs again, but you have also other ones, and you can often formulate as graph on a larger space. You put some additional fields, and up to some coisotropic reduction, you can construct the original Lagrangian manifold, but on the larger space, it's a graph. And in the even case, there are abstractions to do that, related to the Maslov index and so on. And the odd case things are nicer. Actually, you can do it. Okay, so now let me make some observation. Is that as we observed at the beginning, the delta operator, well, say in the finite dimensional case, has nice properties. So in particular, when you compute delta of exponential of something, right, you can factor out the exponential, and here you will have well, delta of this s, and then well, up to sine, you will have 1/2 I h bar square bracket of s with itself. Okay. So now requiring this to be 0 is equivalent to having this expression equal to 0. So I can multiply everything by h bar over I square, and so I will get 1/2 s bracket s, and here, well, up to sine it will be I h bar delta s. Plus or minus, I think plus. So this is the way you write the quantum master equation. I mean, what you need is this expression, but it's nicer to write it this way. And the reason is that if you write it this way, you see that this becomes now a perturbation of the classical master equation, which is what you get when you set h bar to 0. Okay? So the precise thing is that actually you should think of your s as depending on h bar. So there will be some s0 plus h bar s1 and so on. And this equation implies the classical master equation for s0. Okay. And then the idea is that, okay, you might formulate the problem this way. It's easier to look for a solution of this equation. So you look for a solution of this equation, which is an extension of your classical action, and then you try to construct the corrections. And again, this is a perturbation problem, some multiple perturbation problem. Basically, what you can do is that, well, the next, for example, what is the next term? The next term will be S0, S1 plus IH bar delta S0. So which means that if your S0 is delta closed, you're done. But if your S0 is not delta closed, you have to look for some correction. But this equation, by the other property we saw, implies this equation. Right? Delta is a derivation of the bracket, so S0 bracket 0 equal to 0 implies S0 bracket delta 0, 0, which means that even if delta 0 is not 0, it's closed with respect to this operator. And, okay, maybe let me find Q to be the bracket with a 0. This implies that Q squared is equal to 0, so this becomes your differential. So here you have that Q delta S0 is 0. So the bad term is Q closed, and you want it to be Q exact. Okay? So again, if H1 with respect to Q is trivial, there are no problems. And if H1 is non-trivial, there might be potential problems.
And the 0 is the classical action, or like the gauge fix classical action?
S0 is an extension of the classical action that satisfies the classical master equation. Yeah. Yes?
It's like a formal counterpart of a H-bar expansion on loop. This is it seems like a formal counterpart of the perturbative H-bar expansion when expanding loops, and I weighted them by H-bar. When I do a loop computation in a Feynman diagrams, and I weight the loops with H-bar, then I get some kind of effective action weighted by H-bar.
Here, in principle, you have first you have to find this H-bar correction to start with, and then you start the final. So sometimes you really need an H-bar dependent action. The point is that, okay, the nice situation, if this first cohomology is trivial, you can solve the problem. The solution is not unique. I think it becomes unique if probably it's H0. I think, yeah, if H0 is trivial, it becomes unique. Well, of course, this is not true because H0 is really the deformation. So, but apart from the deformation, which means the choice of a coupling constant of the term, this becomes unique. So that means that at the end, in this nice situation, you have your action, right, with some H-bar dependent parameter, which are essentially the coupling constant, which is nice to have already as H-bar dependent because the normalization will make them H-bar dependent, and this is the starting point, and then you start the Feynman diagrams, and you also get the loop corrections. Of course, this assumes that you've done some regularization, blah, 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 and so on. So I will not enter into that you have to make sense of this. Okay, so this is now the idea, and okay, so before I move to the thing, let me tell you that there is maybe one last comment on this before I go back to the connection with the boundary. So that, yeah. Okay, we will not discuss that. There is one interesting extension of this, which is called the BV push forward. So BV push forward means that you do some partial integration. So suppose that you start with the original BV manifold. So this is, for example, in our example was a local perfect. So this is your odd symplectic manifold. And you suppose that it is a product, in a simple situation, of two odd symplectic manifolds. So your omega here is the sum of omega 1 plus omega 2, and delta is the sum of delta 1 plus delta 2. And now what you do is the following. You suppose that you have a function on M that satisfies the master equation. But then what you do is to choose the Lagrangian in here, or the family of Lagrangian in here. And then you construct this, so let me call it L2, and you construct this partial integration. Okay? So this will give you some F twiddle, which is now be a function on M1. Okay, so here I'm a bit sketchy, so if you like in local coordinate, you can make things. If you want to work globally, the correct things to work with is what are called half densities. So in a sense, things becomes more canonical. So you should think of this as a half density, a delta close half densities, and you produce a new half densities up to this, but okay. Just think of functions once you chose the reference things. So the idea is that instead of doing the whole integration in one step, you start doing some integration here. And then you will have to do the residual integration. And now the interesting thing is that maybe a concept assume that delta is 0. You can do this anyway, even if delta f is not equal to 0. The interesting thing is that this operation, well, with the integrated fine, is a delta chain map. If you put a delta here, you can extract it. And so a result is, a consequence is that if delta f is equal to 0, then delta f twiddle is also equal to 0. So it means that if you start with something satisfying the quantum master equation, you produce something which still satisfies the quantum master equation. And the other thing is that if you deform L in here, then f twiddle changes up to f twiddle plus delta, or delta 1 of something. So changing the gauge fixing here changes the effective result by a delta closed term, but delta closed term are completely irrelevant when you integrate them, you get 0. Okay. So this is basically we're saying that BV formalism is compatible with partial integration. So if you apply this to theory, you might think of, say, you have the theory on the whole space. You might think these are like the whole space of fields, and then maybe you split it into infrared and ultraviolet fields arbitrarily. You do the integral over the ultraviolet fields, and you get an effective theory on the infrared fields. And the effective theory still works indeed. Of course, well, if you start here something exponential of S, you get some exponential of some effective action. And, well, formally you start with a local action. Here, typically you get something which is widely non-local, but still you're in the BV setting. And this is one way of making sense of the regularization. This was this proposal by Losev, worked out in some example by Nyoff, and then put somehow in general context by Cattaneo. For a certain class of theories, you regularize essentially your propagators. Typically, your propagators are defined in terms of the green function of the Laplacian. You regularize in terms of heat kernel, and then all this pressure becomes well defined, and then you can do these push forwards and things keep working. And so now you can define the field theory as a family of effective theories, which are now defined on finite dimensional spaces, because the valid fields, and but with compatibility condition. Okay, so this is one way of using this technique to make sense.
So what stands behind delta, the word? Like what kind of math?
Chain math.
Chain, oh yeah, okay. Yeah.
Okay, so I think, okay, it started a few minutes later, but probably there is no more time. And maybe let me say that, okay, just let me, a few minutes say the other things I could say we can discuss privately. So, let me quickly say one thing. One is the BV-VFV connection, and the other one are applications of BV push, other application of BV push forward. So here, what I mean is that, so we say that you start with the solution of the classical master equation, right? And out of it, you produce Q as S bracket, which equivalently means iota Q omega equal to delta S. Right, and so because I write the derivative here, so you see that to produce Q, you have to take derivatives of the action. Right, so typically when you start formulating the problem, you work on closed manifold or you ignore boundary terms. But when you go to the real problem, typically you have boundaries, and so here you have problems in the sense that this equation starts being violated. Okay, by boundary terms. So what happens is that you have to put, as in this Kioski to Chir approach, you have to introduce some boundary terms. Okay, so there are some boundary terms that violate the equation that relate S to Q, and well, you can very nicely geometrically say, suppose that you start with this equation in graded symplectic manifolds, and then you can obtain a lot of consequences. Basically, out of this, you can define some two-form, which has now shifted degree. So here it started in degree -1, this starts having degree 0, and so you see that this starts being related to BFE, and actually under some nice regularity assumption, this will produce some BFE structure on the boundary, which keeps being related to what we have in the bulk by this equation. So you get a nice relation between the bulk and the boundary, and when you do you want to do the functional integral with the boundary, what you do, you have to choose. So here you get like your boundary BFE structure. You have to choose some polarization or some Lagrangian submanifold, and then you all integrate of the fields that match the polarization. And essentially, there is a quantum effect of this equation is that the result becomes a state in the quantization of BFE formalism. So this is one thing. And the other thing, other application of B push forward is that, well, one is this Wilson type definition of renormalization. Another one is the construction of observables, well, extended observables, say on defects. So the idea that you start on some field theory with variable f, right, on some space-time manifold M, and then you want to define some observable on some defect sigma, for example, the Wilson line or some other surface observables. And one way to do it is to produce some other field theory, let me call it X sigma. So this is some other field theory you define on the submanifold with fields living only on the submanifolds, which is coupled to the ambient theory. So here you have your original action, and here you have, so with some field say phi, and here you have like some field psi, and here you have some action as sigma for the theory on the defect, which depends, of course, on its own field, but parametrically also depends on the ambient fields. Okay? Now, what the idea is that now you can think of having the whole space as f m cross f twiddle sigma. So you are in this situation. And you assume that Sm plus S twiddle sigma satisfies the quantum master equation. So if this works, what you can do now, you can take a Lagrangian submanifold here and integrate the exponential of I h bar as twiddle sigma, and this will produce some observable for the original theory. Okay, well, I didn't tell you what an observable is, but let me finish this. So you start with Sm, satisfying the quantum master equation. An observable is some functional O, such that delta exponential I h bar Sm O is equal to 0. Well, the reason is that what you want to do is to compute expectation values, and this equation is precisely the equation that tells that the expectation values will be invariant under the formations of the gate fixing. Okay? And actually, well, this actually boils down to some homology, because if the expression is delta exact, the expectation value is 0. So this tells you that the correct thing, the thing you are really measuring in this BV approach to quantum field theory is the homology generated by this operator. So observe the true physical observable actually elements of the homology of this operator, and then okay, you can produce it. And in this other approach here, then I think that you map observables for the whole theory to observable for the infrared theory, and under some assumption, this mapping becomes an isomorphism in homology. So really, when this happens, actually the effective theory is completely equivalent to the original theory. So, for example, when you go to the effective theory in this sense, somehow you retain all the information of the original theory if you do the proper things to the observables. Okay, so I think I can stop here.
So if you have some classical action and you cannot find a BV action that satisfies the quantum master equation, is this the same statement as a gauge anomaly?
Yes.
Can you see? Can you see non-perturbative or global anomalies in the same way?
Well, this is perturbative, so but now the space of the global anomalies is also that H1. So the space where the anomalies live in this setting and in the other setting is the same. So there is some relation, but yeah.
So maybe I missed it, but the issues with the grip of ambiguity that we have in standard BRST are still here in the BA3.
Yeah. Yeah. I mean, you resolve it well in BRST by saying that even if there is a grip of ambiguity, you can find a section which, of course, intersects the orbits several times instead of just one. And then the argument is more or less topological. The grip of ambiguity is really not a problem because, like, well, the several intersection has essentially up to sign the same contribution, and intersection point, and somehow it's in some sense an odd number, so you only get one contribution. But like they just you don't really have it.
Sorry, can I, just building on the question about non-perturbative anomalies, how do you expect to see non-perturbative effects?
No, here what is only perturbative computations.
Yeah, it seems like the formalism is built for perturbative,
Well,
perturbative deformations and interactions.
Well, when you start computing the integral, typically you do it in the perturbative, but somehow, no, the original geometric thing is also non-perturbative. If you had a way of making sense of the integral non-perturbative, yes, it is there.
But actually, it's like solving the master equation is done in a perturbative way.
Yeah, but that's okay. They're the only assumption that the solution is I mean, okay, you find a formal power series in each part. Yeah, it's still perturbative. Yeah.
So like to what is my understanding so far? We use this method because now we don't have now if I do this what's called saddle point approximation, right? I have a local minima that are all close together on a manifold, right?
Now you have it. Once you do things properly, the assumption, when he said that this is integrable, essentially means that you have the saddle point approximation.
Here comes my question. So suppose that I have a honest to God like global symmetry of my theory, but the group of these symmetries is non-compact. Then I still have the same infinity problem, right? Because now I will have all the many solutions stick together that will give me the same contribution to the path integral.
Yes.
Plus the fact
the volume of the group.
Exactly, the volume of the group, but since it's non-compact, it's infinity.
Yeah, but then somehow, if you think, for example, the partition function as about the normalizing factor for the expectation values, you don't care of an extra factor, because that's what appears everywhere.
On that I completely agree, but so suppose that I truly want to like
cook a
number out of it.
That is some other way, yes.
Okay, so I cannot use BV to...
No. Okay. that factor will still be there.
Sorry, but it's not just the formal series in H bar. Can you actually see the difference between the Lie algebra and the group? If you're
no, you have to put the group information separately. No, this level is everything is all included. You have to put further information there.